Bismillah ar-Rahman ar-Rahim. So in this lecture, we are going to start a new unit about what we call functional blocks. Okay, functional blocks. And this is the outline for this unit. Okay, we'll start by discussing decoders. All right, and then encoders, and they are okay. Remember this when I start discussing the encoders, I will ask you about this. Okay, these encoders and decoders are opposite functions, or they have opposite functions. Okay, and then multiplexers and demultiplexers, they have also opposite functions. Okay, and then we will have some very interesting examples. Let me stop and warn you here. Okay, I need to warn you here because this subject here, from this subject and on, students really lose the focus. Okay, and they find the material very difficult because they don't study and they don't solve problems. Okay, this material is going to be challenging if you don't study. Okay, but if you study and try your best to catch up, okay, in a timely manner, not like before the exam in 3 days you try to catch up. No, this won't work this way. Okay, it won't work this way. This material, it needs time to digest. Okay, it needs time to digest. So you need to work on it on a day by day basis. Okay, otherwise it will be very hard for you to grasp it, as well as the next material, which is about sequential circuits. Okay, that will be more difficult. But once you get this material, you will enjoy it. Believe me, you will enjoy it a lot. Okay, and it is amazing the number of things that you can do when you understand these functional blocks. Okay, all right. So what do we mean by a functional block? This is kind of introduction before we start the components. It's basically a combinational circuit, nothing but a combinational circuit, but it's used, okay, to model some certain functions, okay, and these include, okay, decoders, encoders, multiplexers, and demultiplexers. These are the things that we are going to discuss, but there are other components as well, but we're not going to discuss them. And sometimes in problems, when we say a design problem, sometimes in design problems, we tell you to use functional blocks like multiplexers, or sometimes we say MSI components. Okay, MSI components. Okay, and by MSI components, we mean these components: decoders, encoders, multiplexers, and demultiplexers. Whenever we say use MSI components to implement this function or this functionality, then you know that we mean using these components as well. Also, adders and comparators are part of these components as well. Okay, adders and comparators are part of MSI components, and MSI stands for medium scale integration. Okay, as in comparison to small scale integration. Small scale integration means the basic gates and or I mean these basic gates, but once you move on to medium scale integration, means that you are dealing with bigger circuits. Okay, like these circuits, adders and decoders. So you're dealing with them as functional blocks. Okay, so we have already learned about adders and comparators, and we can use them, as I told you in the previous unit. As I told you, you can use them as black boxes. Again, we are going to continue our components here by discussing the decoders and these 4 components. So as I told you, these blocks are very useful in high level design. Okay, in designing at high level. Okay, when you have to design a large circuit, okay, the K-map method may fail. Okay, For example, your circuit may have 10 inputs, and using KMap for this purpose is really going to be intractable. Okay, it's not possible for you as a human being. Maybe for computers it's okay, but for you it's not going to be possible. Okay, so we need to think at a higher level, at the level of components or functions. Okay, these days the functional components, these functional components, okay, as are part of what we call design libraries. Okay, so you have a design library as a designer, as an engineer. Okay, you have a design library at your disposal. Okay, and you can use any of these components as is. Okay, you can use it as is, and these components are very well tested, and they are known to work very well. I mean, you can reuse them as many times as you need. Okay, so when you have a library, it is supposed to contain some of these components, some of the one variation of each one of these components. Okay, and then if you need another variation, for example, you're using a small decoder and you need a larger decoder, then you build it from the smaller decoder. Okay, that's why we will see that we're going to teach you how to build larger decoders from smaller ones. Anyway, let's get started with decoders. Okay, the first circuit in functional blocks. Okay, so what do we mean by a decoder? Just pay attention to the behavioral description of the decoder. Okay, a decoder, we call it, this is the name of the decoder. It goes like this: an N to 2 to the N decoder, N to 2 to the N decoder. So maybe N is 1. If N is 1, then it's 1 to 2. If N is 2, it's 2 to 4, and so on and so forth. So this is the number of inputs, and this is the number of outputs. Okay, in the decoder. Okay, so it tells us, the name tells us how many inputs and how many outputs in the decoder. Okay, it's like this. You see it here. You have N inputs and 2 to the N outputs. Okay, and you have an it's not N bit actually. It's just like this: N to 2 to the N. So let me try to update this. So it's N.
Doctor.
Yes, to 2.
Is this
decoder? Yes.
Does this has the same 64-bit decoders used online, like on a website?
What's that? What is that? Can you tell me more about it?
It's just a website. For example, if you have a link, you enter the link and it will decode it for you, and you can encode it.
So
is this the same? Or
URL shortener, you mean?
Not a shortener, just an encoder and a decoder, 64-bit encoder. So if you want to encode the link, you have a YouTube link, for example, it will encode it for you, and you send it to someone, and he can encode it later on.
How do you encode it? You just paste it into the browser, right?
Yes, you just paste it into this website.
It's a URL shortener then. I mean, the 64-bit, it's different. It's the same concept of decoding. Decoding means mapping, by the way. Decoding means mapping. Okay.
It's considered the same?
No, they are not considered the same. So that one is a substitution. Okay, but here we are also substituting. Okay, but it's a very specific kind. It's a binary decoder. Okay, a binary decoder. We will see once you understand this. Just compare it with what you know. Okay.
Okay.
So basically, yeah.
Sorry for interruption. I just want to make sure about the decoder. Is it the same can I say, for example, decrypt? When I say decrypt, is it the same when I say decode? And this?
No, it's not. No, it's not related to encryption. Do not confuse that with this. Okay.
Okay.
It's not related to encryption. Okay. So a decoder here means a mapping. Okay. So you have an n bit input and 2 to the n bit output, and there is a mapping in between. And this relationship between the input and the output is defined like this. D, which is the output, is equal to the A, which is the input. Maybe this A should have been a big case A so that they match here. But anyway, you get the idea anyway. Okay. So if your input is A, little a, then your output is nothing but 2 to the A. What does 2 to the A mean? 2 to the A means 1 in binary. 1 followed by how many zeros? A zeros, right? So in your output, how many ones are there?
Only one.
Only one. Exactly. One output at any time is going to be 1. And it is going to tell you exactly what was your input, because the position will tell you, the position of this one will tell you which input or what was your input. So the input basically tells me the position of the output that will be 1. Okay. All right. So for example, if A is 1 0 in binary, then D is going to be, of course there is a 0 on the left here, but I'm not writing it, 0 1 0 0, right? Because it's 2 to the 2, which is in binary 1 0 0 4. It's 4. This is 4. Okay. So 2 means that bit number 2 is on in the output. So 0 1 2, right? And 3 means bit number 3 in the output is on, 0 1 2 3. So 2 to the 3 is 8, and in binary it's 1 0 0 0. Do you see that? It's important to understand the behavior before we move on. Okay. So the input A tells us precisely which bit of D is on. Okay. This is in simple terms. This is the output. This is the decoder and how it functions. Okay. So if I give you this information here, can you use your knowledge that you gained in unit 7 and design the decoder or implement the decoder? Use the design procedure to implement the decoder? Answer is, I'm sure, yes. Okay. Because how many inputs do you have? A is n bit, right? And D is 2 to the n bit. Okay. And you do have the formula that relates the two, and then you can derive the truth table, and then for each output derive a k-map, and then minimize for each output, and then derive a formula for each output. That's it. Okay. All right. So the derivation of the function of the implementation of the decoder, we are way beyond that now. Okay, we are way beyond that. We assume that you already know how to do that. Okay, but we are going to show it anyway. Yeah, so let's take an example before we move on to implementation details. Okay, in 4-bit decoder, okay, if input is 12, okay, then we know that bit number 12, okay, of D is going to be 1, whereas all other bits of D are zeros. Okay, this is to reiterate this concept here. Okay, you see that? So I'm sorry. Again, I did a mistake. It's not 4-bit. It's a what? Who can tell me? A 4 to 16, which is 4 to n, 4 to 2, which is actually 4 to 2 to 4, which is 4 to 16. Okay, in a 4 to 16. So the decoder has how many outputs? 16 outputs, and we know from if the input is 12, then bit number 12 is going to be 1. okay? And all other output pins are going to be, or bits are going to be 0.
Doctor, isn't it supposed to be one output with 16 bits?
Yeah, it is. It is actually, yes. Okay, yeah, you can think of it like this. Okay, they are both the same. So your output is 16-bit wide, or you have 16-bit outputs, yeah, or 16 outputs, each of 1 bit. That's up to you to interpret. Okay,
Yes.
so now. This is just to reiterate what I just said here, okay, is that only one output of the decoder is going to be 1 at any time, okay, no matter what the input is, okay? And the process of converting A to D is called decoding. It's just a mapping, okay, mapping between the 2 domains here, okay, A to D. The process of converting A to D is called decoding, okay? Yeah, okay. So if we don't use some input patterns of A, then the decoder may have less than 2 to the n outputs. For example, if you have 4-bit input, but your input range is a BCD, for example, BCD number. Okay, actually BCD, yeah, BCD number. How many outputs do you have? How many outputs do you have in this case? You have 4 inputs still. It's 4 input, but how many outputs do you need to represent the BCD input? So how many possibilities do you have? And then you decide on the number of outputs, right? How many possibilities?
From 0 to 9, so 4-bit would be enough.
I'm not talking about input. 4-bit is fine for input, okay? But for how many outputs do you have? For a BCD?
16.
No, not 16.
10.
It should be
it should be 10.
less.
Should be 10. 10, exactly 10, because your input does not exceed 10, does not exceed 9, in fact, okay? It does not exceed 9, all right? So the maximum input is 9. So if you get more than 9, then this is beyond your capability, and you shouldn't output that. You should blame the whoever supplied this input to you, okay? So this is basically what this bullet says here. So if we don't use use some input patterns of A, then the decoder may have less than 2 to n input. Yes, question.
How do we name it if it's BCD?
Yeah, it's 4 to 10. You can say 4 to 10. Okay, we use 4 to 10 decoder. Yeah, but this is rare. I mean, we don't usually use it anyway. But it is used. Okay, so what is inside this block? As I told you, you guys know how to. Again, I just copied this from previous. This is N to 2 to N. Okay, decoder. All right. How do we know what's inside? Basically, you can use design procedure to get what's inside, and these slides are taken from Dr. Mudawwar's slides, okay, and this is showing you how to derive the truth table of a 2 to 4 decoder, okay. So in 2 to 4 decoder, we have the input patterns from 00 to 11, okay, and then we have the D's from D0 to D3. Okay, when your input is 00, it means that D0 is on. Okay, this is D0, and the rest are off here. Okay, and when it is 01, then D1 is going to be on, and the rest are off. All right, 10, D2 is going to be on, and the rest are off, and D3 is going to be on, and the rest are off. So in a way, A is going to tell you what is the index of the output that is going to be 1. Okay. So this is the truth table, and to implement D0, we know basically that D0 is nothing but minterm number 0. Okay, you don't need a K-map for that. Okay, this is trivial. All right, and so what is D0? It is going to be, who can tell me? So we have in canonical form. Who can tell me what is D0 in canonical form? It is nothing but,
You mean A1, A0?
in terms of A1 and A0. Yeah. What is a D0?
A complement, A0 complement.
Yeah, exactly. So it's A1 complement ended with A0 complement. What about D1? A1 complement.
A complement,
A1 complement, A0.
Yeah, come on. This is revision, and then you just finished the midterm exam. Have you formatted your memory already? You should remember this already. Okay. So anyway, maybe you're shy or something. 1 0. Okay. Here, this one here. Okay, it will be A1 A0 complement. Okay, and this one will be A1 A0 for D3. Okay. Similarly, you can see for the 3 to 8 decoder, 3 to 2 to 3, which is 3 to 8. Okay, it has 3 inputs and 8 outputs. Okay, from D0 to D7. Okay, you can see that the decoder D0 is nothing but minterm number 0, and D1 is going to be minterm number 1, and so on and so forth. So each decoder output is going to be your minterm. Okay, the corresponding minterm. Okay, so again, the material is very connected to each other. And the final, although we don't ask you in the final about specific questions about the previous material, but you should understand the previous material in order to understand the current. Okay. All right. So minterms and maxterms are essential for understanding decoders. Okay. So you know that D0 is nothing but minterm number 0, and D1 is going to be minterm number 1, and D sub I is going to be minterm number I in general. Okay, for any decoder of any size, the output number I is going to be minterm number I as a function of the inputs. However, you must understand that the inputs are weighted here. Okay, they are given weights, and you must know that A2 here has the highest weight, and A1 has the second highest weight, and A0 has the lowest weight or least significant bit. Okay, remember, if you remember when we did the minterms, I told you that F of A, B, and C, right? And I told you that the order matters when you write it in canonical form. Do you remember that? Yes. Okay, do you still remember this? The order of the literals here matter very much, okay? Because M0, okay, if you say M0 here, okay, with respect to this order, M0 will not be different, but M1 will be different. Let me say M1 is going to be what with respect to this order now?
A with B complement,
B complement, C.
A complement, B complement, C, right? But if the order was F of C, B, A, then M0, M1, I'm sorry, is going to be what? C complement, B complement, A. It's different. It's completely different, okay? The same thing goes with the decoder, okay? You must give the input, okay? The input that you need, you must give it the weight that you need, okay? And since decoders gives us minterms, we know immediately that they can be used to implement Boolean functions. And then actually this is a subject that follows this. Okay, after this, I'm going to discuss implementation of Boolean functions using decoders, because all you need is an OR gate, okay, at the output or the minterms that you want, of the decoder, and then you get your function. That's it. Okay. So,
Doctor.
but before we do that, let me see what is inside now. This is, as I told you, it's just a Minterm, right? And this is the 2 to 4. Okay, it's nothing but a bunch of AND gates. Okay, 4 AND gates. Okay, D0 is going to be A1 complement, A0 complement, and so on and so forth. Okay, so each decoder term or output, each decoder output is a Minterm, and you can see the same thing here goes for the 3 to 8 decoder. Again, this slide is taken from Dr. Mudawwar's slides. Okay. So the important observation here is that each decoder output is a Minterm. Okay, let's challenge ourselves. What is a Minterm? Minterm is a product term in which all the literals appear, right? In complemented or uncomplemented form. You can see here that all the literals appear of the input. Okay, in all the cases. And here, all the literals appear, 3 literals. In each case, there are 3 literals. Okay. So each one of them is a Minterm. Okay. Now it is natural to ask yourself, since the decoder output is a Minterm, I can use it to implement functions. Okay, Boolean functions. Okay, just like we did with the what we call the canonical form. Okay, so but before that, note that we can use, instead of AND gates, okay, here we can use NAND gates. Okay, sometimes this is a variation of a decoder. It's called the NAND decoder. Okay, and the purpose of that is to output the Maxterms instead of Minterms, because if you have studied very well for the midterm, you should know that MI is equal to what? The complement of
Maxterm.
Yeah, the Maxterm, right? So if you complement these AND gates, the output of these AND gates, okay, you complement it, you put bubbles here and use NAND instead, you'll get the Maxterms instead of the Minterms. Okay, so this is a variation of the decoder that you can get. Okay, so now we switch to implementation of functions using decoders. Okay, so we would like to implement this function f of a, b, c. Okay, which equals the sum of these Minterms 1, 2, 6. Okay, using 3 to 8 decoder. Okay, so here is my 3 to 8 decoder, and you can see that my C is the least significant bit here, so it's hooked up to my A0, which is the least significant bit input of the decoder. You can do it this way, either A0, A1, A2, or you can say 2 to the 0, 2 to the 1, 2 to the 2, just like we did here. Okay, both are fine. Okay, so here I'm indicating that this input here, this C here, is hooked up to the least significant bit of the decoder input. And A is connected to the most significant bit, just like your function. Okay, your function. And then what happens at the output, you take the Minterms that you have and then you OR them. That's the sigma notation, right? So we take D1, 1 and 2 and 6, and then we OR them together and we get our function. Okay, so notice again, it is very important to notice the correspondence between the inputs. Okay, the weight of the input and the weight of the function input and the weight of the decoder's input. Okay, they must match, otherwise your output will not be correct. Okay, any question here?
If they ask me to write the expression, do I have to write it in canonical form, or can I simplify it, for example?
Of course, no. You have to, it has to be in canonical form. If it is simplified, then you express it in canonical form, because you need to know the minterms. You need to know the minterms to decide on the output of the decoder to use. Okay, so once you know the minterms, you can construct it using a decoder. Okay, good question. Okay,
Doctor.
yeah.
Why do I need to list the other decoders? I don't have them anyway. I only need 1, 2, and 6.
What's that? Come again?
Regarding the decoders, do I need to list them all? I only need 1, 2, and 6. The others will be disregarded anyway.
If I'm the one who's grading, I don't mind, but because I'm not sure who's grading this, just list them all. Okay.
Okay.
All right. So just to be on the safe side, list them all. Okay. This is not a pain, by the way. The pain is when you have to draw a 4 to 16 decoder, because you have 16 output. Okay.
Yes, that's why I'm asking.
Yeah. Okay. Okay. So now, if the number of minterms that are summed is large, then we take the max terms instead. Okay. So here is an example. If you have use a decoder, a 3 to 8 decoder to implement this G, okay, and notice that here I'm using G of C, B, and A, okay, instead of A, B, and C, okay, which equals the sum of these minterms from 1 to 6, okay, and this equals in our from our previous knowledge, this equals the product of these two max terms, okay. So all you have to do, okay, is to basically take the product here, this one here, okay, and then NOR it with this one here. Okay, why is this the case? Because if you push back this bubble, this one will become AND, okay, all right, and this will become max term number 0, and this will become max term number 7, just like here. We are ending max term number 0 and number 7. You get it? So this is why M0 ended with M7. This is what this equals, and this is nothing but M0 complement ended with M7 complement, and by De Morgan's law, this is nothing but M0 NORed with M7. Okay, so this is why you get an OR here instead of an OR. Okay, so if you have a large number of minterms, then you basically take the other minterms, the remaining minterms, and you NOR them instead. Okay, instead of ORing. That's the whole idea. And then notice here that I'm connecting A to the least significant bit and C to the most significant bit, because it is indeed C that is the most significant bit here. Okay. And also notice that one decoder can implement many functions, not just one function. Okay, because you have access to all of the minterms, and you can construct as many functions as you want. Okay, so this is an example here that we are constructing, for example, 3 functions. And who can tell me what are these functions in canonical form? So this one is, let's call it sigma of what? Who can tell me what is this?
0 and 1.
0 and 1, excellent. Okay. And this one, the second one, what is it?
Max term of 3 and 5.
Max term 3 and 5. Yeah, excellent. And this one is sigma. I feel that this is easy, but when it comes to reality, okay, believe me, if you don't review it, you will forget it. It is easy. It is very easy, but you should not forget it. Okay. All right.
Doctor.
Yeah.
When implementing the function or taking the output, does it always have to be in sum of minterms? You can't do it.
Your mic is muffling. Can you repeat your question, please?
I said when implementing the function, does it always have to be in sum of minterms form?
Yes, this is what one of your colleagues have asked the question. So if it is not, then you have to change it to a max term, I mean canonical form. Okay.
Okay. Yes.
All right. Okay. What about some decoders? They have what we call an enable function. Okay? Enable input. Okay. In addition to A, they have an enable input. So enable basically, if enable is 0, okay, the decoder output will be 0. All right. All the outputs will be 0. Okay. And if enable is 1, the decoder will function normally. Okay. So I haven't added anything except just an input here. Okay. Again, this is a slide from Dr. Mudawwar's. Okay. An input here, which is called enable, that will enable or disable the decoder. If it is 0, then the output will be 0. If it is 1, then the output will be the normal output of a decoder. And you can guess how to implement that by adding the enable with the minterms, with all the minterms. Okay, so this is the truth table. If we have 0 for enable, then A1 and A0 are don't cares, and we have 0 output for all the outputs. Okay, if my enable is 1, then the decoder functions normally. Okay, this is the normal function of the decoder. This kind of decoders will help us implement larger decoders from smaller decoders. Okay, and yeah, and the process of doing this is called decoder expansion. Building larger decoders from smaller ones is called decoder expansion. Okay, and this is the slide below shows how to construct a 3 to 8 decoder from 2 to 4 decoders. Okay, from 2, actually from 2, a count of 2 to 4 decoders with enable. Okay, and 1 to 2 decoders. Okay, 1 to 2 decoder. So what happens here is that we have this 1 to 2 decoder, which is nothing but, by the way, an inverter here. And so you take A2 and invert it or take it as is. Okay, this is a 1 to 2 decoder. It's nothing but an inverter. So you invert the input or you don't invert the input. That's when you have 1 bit input, you only have 2 minterms. Okay, either A complement or A. That's it. Okay, so when A2 is 0, we are enabling this top decoder. Okay, which is so pink. Okay, the pink decoder. When A2 is 0, okay, we are enabling the top decoder and disabling the yellow decoder. Okay, when A2 is 0, we are disabling the yellow decoder and enabling the pink decoder. When A2 is 1, we are disabling the pink decoder and enabling the yellow decoder. So this decoder, although the outputs here are 0, 1, 2, 3, D0, from inside, and here it's the same D0, D1, D2, D3. However, from outside, you should think of it as the outputs of the 3 to 8 decoder. So this is D0, D1, D2, D3, and then D4, D5, D6, D7. Okay. So this is the function table or the truth table. Okay. You can see that A2 controls which decoder, which 2 to 4 decoder is going to be selected or enabled. Okay, is it the pink one when A2 is 0? So pink one will work, and the other one will be zeros, all zeros here. Okay, and if it is 1, if A2 is 1, then the yellow one will be enabled, and the pink one will be all zeros. Okay, you get that?
Doctor.
Yeah.
I don't get why are we disabling one and activating the other one while they are both 2 to 4. Because if A2 is 1, so at max it would have 6 as a number.
Let me ask you this.
And-
Let me ask you this. So look at this. Look at this table. Okay. What
Yes.
does it show you? As a whole, just do not disregard the circuit on the right. What does it implement to you? These are the inputs and these are the outputs.
8-bit decoders
No, it's not 8-bit. It's not called 8-bit.
from 3 to 8.
3 to 8 decoder. Excellent. So we are basically implementing a 3 to 8 decoder from smaller decoders. Okay. So the output of the 3 to 8, we have to have 8 outputs. Okay. So we have 2 to 4 decoders here. That gets us the 8 outputs that we want. But then we have to enable this for half of the time and enable this for the other half of the time. Okay. So for the top part of the truth table, when A2 is 0, okay, this decoder, A2 is 0, this decoder is going to be enabled. Okay, A2 is 0, so this is 1. Okay, so the enable is 1 here, right?
Yes.
When enable is 1, this decoder is working. And notice that this is these two signals, this one and this one, are the complement of each other. So one of them is 1, then the other is 0. So this is going to be disabled. Okay?
Output will be 0. Yes, I see now.
Yeah. So this is why it's called, we are implementing the 3 to 8 decoder from 2 to 4 decoders and 1 to 2 decoder. Okay?
Yes, I see now.
So let's just reinforce this information by giving another example of building a 4 to 16 decoder with enable now, with enable. All right. We would like to implement it with enable from 2 to 4 decoders with enable. The only difference here is that you are going to replicate this how many times? 4 times instead of just 2 times, because you need 16 outputs, right? And then instead of 1 to 2 decoder to select select one of the 2, you need 2 to 4 decoder to select one of the 4. Okay, so here this is one of the 2 to 4 decoder to select one of these decoders. Okay, of the level 2 decoders. Okay, so only one of them will be active at any time. Okay, depending on A3 and A2 of the selection. Okay, so these are the most significant bit of the decoder, of the 4 to 16 decoder. And these are going to be the least significant bit, 2-bit, of the 4 to 16 decoder. And notice that they are all shared between all the level 2 decoders. Okay? So once, for example, if this is 0, 0, then we have a 1 here and 0 here and 0 here and 0 here. Okay? So this decoder is going to be enabled. If we have a 0, 1 here, okay, then this is going to be enabled and the rest are going to be disabled. Okay? And we also have an enable here because the requirement here is to build a 4 to 16 with enable. If it wasn't with enable, then we don't need this enable. Okay? Do you get that? So all we need, if it wasn't with enable, then all we need is a normal decoder without any enable input. Okay? But we need the enable as part of the requirement here, build the 4 to 16 with enable. Any question?
Yes, doctor. For the decoder that determines the enable value, is it always the inputs of it have to be the most significant bits?
Yes, it is always that. Yes, you're absolutely right. Exactly. So as the more you go to the left, okay, maybe you have 3 levels, by the way. You can have 3 levels. Okay, the more you go to the left, okay, the more significance your input bits are. Okay.
Yes.
All right. Actually, it shows you which part of the, so this part is the top quarter of the table, and this part is the second quarter of the table, and so on and so forth, of the truth table, I mean. So I'm going to stop here because the lecture is over. stop recording.